You turned on a light switch today. Maybe this morning, maybe a few hours ago. You flipped it, and the room filled with light. And you probably didn't think about it for even half a second. Why would you? It's just light. It does what it does. But here's the thing, and I want you to really sit with this for a moment. The light that filled your room travelled from the bulb to your eyes at a speed so extreme, so fundamentally bizarre, that the greatest minds in human history spent centuries not just failing to understand it, but failing to even ask the right questions about it. And when we finally did start asking the right questions, the answers broke physics. Literally. The answers broke the version of physics that had worked perfectly for 200 years. That's not an exaggeration. That's what happened. If you enjoy videos about space, physics, and the genuinely weird stuff hidden inside ordinary science, I'd really appreciate it if you subscribed and liked the video. It genuinely helps the channel grow, and it means I can keep making these. Now, get comfortable. Seriously, make a cup of something warm, find a good spot. Let's begin. Okay, so let's start with the thing everyone gets wrong. And I mean everyone, not just people who don't study physics, but people who do. Even people who teach it sometimes frame it wrong. The common understanding of the speed of light goes something like this. Light is the fastest thing in the universe. Nothing can go faster. It's the cosmic speed limit. And if you somehow broke that limit, well, you'd travel back in time, or the universe would explode, or something bad would happen. That version of the story is not wrong exactly, but it's like saying a black hole is a big hole in space. It's pointing in the right direction, while completely missing what's actually strange about it. Here's the misconception buried inside that story. People treat the speed of light as if it's a speed limit that was imposed on the universe. Like someone sat down, decided that light goes fast, set a number, about 300,000 kilometers per second, and said, okay, that's the max, nobody goes faster, as if it's a posted sign on a cosmic highway. But that's not what the speed of light is. The speed of light isn't a speed limit. It's more fundamental than that. More structure. More strange. The speed of light is the speed at which information, any information, not just light specifically, propagates through space. It's the rate at which cause produces effect. It's embedded in the fabric of space and time in a way that makes it not just a number, but something closer to a defining property of reality. And here's where it gets really strange, because this is the part most people genuinely haven't heard. The speed of light isn't just fast. It's the same. Always. For everyone. No matter where you are, no matter how fast you're moving, no matter what direction you're going, if you measure the speed of light, you get the same number. That sounds almost boring when I say it that way. Yeah, okay, it's always the same. So what? But think about what that means. Really think about it. If I throw a baseball at you, and you're standing still, the ball is going, say, 90 miles an hour relative to you. Now, if you start running toward me, while I throw it, the ball is going faster relative to you, maybe 95 or 100 miles an hour. That's just how speed works. Velocities add together. You learned this in school. Now replace the baseball with a beam of light. I shine a flashlight at you. The light is travelling at 300,000 kilometers per second relative to you. Now you start running toward me at, let's say, half the speed of light, just for fun. How fast is the light beam moving relative to you now? If velocity worked the way we expect, it would be 300,000 plus 150,000. That's 450,000 kilometers per second. But it's not. It's 300,000. Exactly. Same as before. Same as always. Same as it would be if you were standing perfectly still. Same as it would be if you were running away from the light. Same. That's not just strange. That's the thing that broke physics. Let me take you back in time for a bit, because understanding why the speed of light is strange requires understanding what the world thought before we knew how strange it was. For most of recorded human history, the question of whether light had a speed at all was considered basically philosophical, not scientific. There was no obvious way to measure it. It was just light. It appeared when the sun rose, it disappeared when it set, it came out of fire and candles, and when you opened your eyes, it was just there, instantaneous. No delay, no signal. Aristotle thought light was instantaneous, that it had no speed at all, because it didn't travel, it just existed or didn't exist. And honestly, for the technology of ancient Greece, that was a completely reasonable conclusion. You can't observe the speed of light with the naked eye. You can't watch it arrive. This view held for a very long time, a very, very long time. Until the 17th century, most serious thinkers, people who were doing what we'd now recognize as early science, genuinely believed light was either instantaneous or moved so fast that measuring it was impossible. Then came Galileo. Now, Galileo didn't measure the speed of light, but he was the first person we know of who actually tried to. His method was beautifully simple and completely doomed to fail, but let's appreciate it anyway. He stood on one hill with a lamp. His assistant stood on another hill, maybe a mile away. Galileo would uncover his lamp. The instant the assistant saw the light, he would uncover his lamp in response. Galileo would time how long it took to see the return light, subtract his own reaction time, and that was the round-trip travel time of light. The result? He couldn't measure anything. The delay was too small, if it existed at all. Galileo concluded, correctly, that if light had a speed, it was at least 10 times faster than the method could detect. He wasn't wrong, he just didn't have the tools. The actual first measurement, or rather the first solid evidence, came from a Danish astronomer named Ole Romer in 1676. And the thing is, Romer wasn't trying to measure the speed of light. He was trying to make better tables of when Jupiter's moon Io would go into eclipse, for navigation, for sailors. That's all. What he noticed was strange. The eclipses of Io weren't happening on schedule. When Earth was on the side of its orbit closer to Jupiter, the eclipses came a little early. When Earth was on the far side of its orbit, when Jupiter was further away, the eclipses came late, by about 22 minutes total, and Romer had the insight to understand what that meant. Light was taking longer to reach Earth when Earth was further from Jupiter, which meant light had a finite speed. And from the 22-minute discrepancy and the diameter of Earth's orbit, he calculated something in the range of 220,000 kilometers per second, off by about a third. His measurements of Earth's orbit weren't quite right, but the principle was there. The first real measurement of something we had assumed was infinite. Think about what that moment was. An astronomer, trying to help sailors navigate, accidentally measured one of the most fundamental constants in the universe. While looking at a moon of Jupiter, while that moon went behind Jupiter in a pattern that had nothing to do with the question he was asking. Science does this. It sneaks up on you from the side. Now, Romer wasn't universally believed. The prevailing view among European astronomers for decades after his paper was divided. Some accepted it, others, including the formidable Giovanni Cassini, who had actually collaborated with Romer on the Io observations, rejected it. Cassini didn't think the timing discrepancies were caused by light travel time. He thought they were observational errors. The debate wasn't settled until 1729, when the English astronomer James Bradley discovered the aberration of starlight, a slight angular shift in the apparent position of stars that depended on the direction of Earth's orbital motion. This, too, implied a finite speed of light, and Bradley's calculation gave 298,000 kilometers per second, closer to the truth. Romer was vindicated 50 years later by someone who wasn't even looking for the same thing. This is a pattern that repeats in the history of the speed of light. Someone discovers something for one reason, and it turns out to be about something much deeper. The next great chapter in the direct measurement of c came in 1849, and this time it happened in a lab. A French physicist named Hippolyte Fizeau built a device specifically to measure the speed of light on the surface of Earth. He aimed a beam of light at a rotating toothed gear, thousands of teeth, spinning at high speed, and through the gaps between the teeth, the light travelled about 8 kilometers to a mirror on a distant hilltop and reflected back. If the gear was spinning at exactly the right speed, the returning light would pass back through the same gap it left through. If the speed was slightly off, the returning beam would be blocked by a tooth. By adjusting the rotation speed until the light made it back cleanly, Fizeau could calculate how long the round trip took. His answer: approximately 313,000 kilometers per second. Not perfect, but remarkably close for a terrestrial measurement in 1849. What's remarkable about Fizeau's experiment isn't just a number, it's the approach. He was measuring the speed of something we can't see, using a device made of brass gears and mirrors on a dark hillside outside Paris. There's something wonderfully, stubbornly human about that. We wanted to know how fast light went, and we built a machine and figured it out. Léon Foucault improved on Fizeau's design a few years later, replacing the toothed gear with a rotating mirror. His technique was more controllable and eventually gave values much closer to the modern accepted figure. And from Foucault onward, successive generations of physicists refined and refined, using better equipment, longer baselines, eventually laser interferometry, until by 1983 we had pinned the value down with such precision that we did something unusual: we reversed the definition. Since 1983, the meter is defined as the distance light travels in a vacuum in 1/299,792,458 of a second. The speed of light isn't measured anymore, it's defined. It's exactly 299,792,458 meters per second by international agreement, and if your ruler disagrees, your ruler is wrong. The constant has become the standard. That's a strange kind of closure. We spent 3 centuries trying to measure something, and when we finally measured it precisely enough, we made it the foundation of measurement itself. Even now, even after all of that, we're still finding out what it means. Even with Romer's measurement, nobody had any idea what was strange about the speed of light. They had a number, a very large number, but just a number. Like, okay, light goes fast. Great, move on. The strangeness didn't start to become apparent until 2 centuries later, when physicists started asking deeper questions about what light actually was. Here's a quick version of the puzzle they ran into. By the mid-1900s, a Scottish physicist named James Clerk Maxwell had figured out that light was an electromagnetic wave. He developed these 4 beautiful equations, Maxwell's equations, that described how electric and magnetic fields interact. And when you work through the math of those equations, they naturally predict that electromagnetic waves travel at a specific speed, a speed that falls right out of the equations, about 300,000 kilometers per second, which is the speed of light. Obviously, that's not a coincidence. That's how we confirmed light was electromagnetic. But here's the problem. The speed that Maxwell's equations gave you, it wasn't relative to anything. It didn't say light travels at 300,000 kilometers per second relative to the source. It didn't say relative to the observer. It just said 300,000 kilometers per second. Absolute, fixed. In 1865, that was a crisis waiting to happen. Because at that time, everyone believed in something called the luminiferous ether. The ether, an invisible, perfectly still medium that filled all of space, through which light, being a wave, had to travel. Because waves need something to wave through, right? Sound waves travel through air, water waves travel through water, so light waves must travel through something. The ether was that something. Nobody had detected it. Nobody had any idea what it was made of, but it had to be there, logically, because waves need a medium. And if the ether existed, this perfectly still fabric of space, then Maxwell's 300,000 kilometers per second was relative to the ether. Not relative to the observer, which meant that if you were moving through the ether, you should detect light going slightly faster or slower depending on your direction relative to that motion. This was testable. This was specific. This was science. In 1887, two American physicists, Albert Michelson and Edward Morley, built an incredibly sensitive instrument to detect this effect. Called it an interferometer. The idea was, they'd split a beam of light into two beams going perpendicular directions, let them travel and bounce back, and then recombine them. If light was being carried by the ether, and Earth was moving through the ether as it orbited the Sun, then the two beams should come back at slightly different times. The interference pattern would shift. They ran the experiment and ran it again and again. Nothing, no shift. No difference. The speed of light was the same in every direction. This result was catastrophic. For physics, there was no other word for it. The experiment that was supposed to confirm the ether and explain how light waves travel, instead found nothing. No ether effect. No difference. Just the same speed, over and over, no matter how they oriented the apparatus. People tried to explain it away. Maybe the Earth dragged the ether along with it. Maybe the apparatus contracted as it moved. Lorentz and Fitzgerald proposed exactly this, a physical contraction of matter in the direction of motion, as a way to explain the null result. They called it the Lorentz-Fitzgerald contraction. They weren't wrong. That contraction is real, but they didn't understand why yet. They were reaching for an explanation from within the old framework, not realizing the old framework was the problem. It took another 18 years, and a 26-year-old patent clerk in Bern, Switzerland, you know his name. Einstein didn't approach the problem by trying to explain the Michelson-Morley experiment. He approached it from the other direction, entirely. He started with two postulates. Two assumptions he decided to treat as true and see what followed from them. First, the laws of physics are the same for all observers moving at constant velocity. No special reference frame, no privileged position. A physicist in a train moving at 60 kilometers per hour does physics the same way as a physicist standing on the platform. There's no experiment that can tell them who's really moving. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. That's it. Two simple-sounding statements. And from those two statements, in a short paper published in 1905 on the electrodynamics of moving bodies, Einstein derived special relativity. He derived time dilation, length contraction, the relativity of simultaneity, E equals mc squared, the whole package. But I want to stay on that second postulate for a while, because it sounds simple, but it's not. It's the most radical statement in the history of physics, and I want you to feel how radical it actually is. The speed of light is the same for all observers, regardless of their motion. Let's really build this up slowly. Imagine you're standing on a train platform. A train comes through at half the speed of light. On the train, a passenger points a flashlight forward in the direction of travel and switches it on. How fast is that light moving relative to you? Your instinct says, well, the train is going half the speed of light, and the light is moving at the full speed of light relative to the train. So relative to me, the light must be going at 1.5 times the speed of light. You're adding velocities. Completely natural. Completely how it works for everything else. But no, the light is moving at exactly the speed of light relative to you. Same as if the train was standing still. Now, think about what that means for the passenger on the train. They turn on the flashlight. The light moves forward. From the train's perspective, the light moves at the speed of light, 300,000 kilometers per second ahead of them. From your perspective on the platform, the light is also moving at 300,000 kilometers per second, not 450,000, not more. The same, but the train is also moving at 150,000 kilometers per second relative to you. So from your perspective, the light is moving at 300,000 kilometers per second. The front of the train is moving at 150,000 kilometers per second. The light is getting ahead of the train at a rate of 150,000 kilometers per second. But from the passenger's perspective, the light is moving at 300,000 kilometers per second relative to them. It's getting ahead of them at 300,000 kilometers per second. Same light, same beam, two different observers. Two different measurements of how fast the light is pulling away from the train. Both are correct. Here's the strange part. The only way both can be correct simultaneously, and this is where Einstein's genius comes in, is if time itself is passing at different rates for the two observers. The passenger and the platform observer don't just disagree about the speed of the train, they disagree about time, they disagree about distance. They exist in slightly different versions of time and space, and both versions are equally valid. There's no absolute time, there's no absolute space. The only thing that's absolute, the only thing that's the same for everyone, is the speed of light. Let that breathe for a second. The speed of light is constant. And in order for it to be constant, time has to be flexible. Space has to be flexible. Our ordinary intuitions about what simultaneous means, about what now means, about what distance means, all of that had to give way so that the speed of light could stay fixed. It's as if the universe decided the speed of light is non-negotiable. Everything else can bend, and everything else does bend. Time dilation is real, measurable. We measure it constantly. The GPS satellites orbiting Earth experience time running at a slightly different rate than we do on the ground, partly because of their speed, which slows their time relative to us, and partly because of the weaker gravity up there, which speeds back their time relative to us. We correct for both effects. If we didn't, GPS would drift by about 11 kilometers per day and become useless. That's not theoretical, that's engineering. Your phone's Maps app works because we understand that time runs at different rates for objects moving at different speeds. But okay, let's go deeper, because the constancy of the speed of light isn't just strange in the way I've described so far. There's another layer, and I think it's somehow even stranger. Why 300,000 kilometers per second? Why that specific number? Why not faster? Why not slower? Why not 10 times faster? 1,000 times faster? Here's where I want you to sit with something that physicists don't usually spend much time on, but which I find almost unbearably interesting. The number 300,000 kilometers per second, or more precisely, 299,792,458 meters per second, isn't arbitrary in one sense, but it is in another. The specific value depends on how we define our units. If we measured distances in feet instead of meters, and times in minutes instead of seconds, the number would be different. The units are human-made. The speed itself isn't. But the question remains, why is it what it is? Why is the universe's maximum signal speed, the rate at which cause and effect can propagate, set to this particular value? And the honest answer is, we don't know. We can measure it, we can derive everything else from it. But we can't, yet, at least, explain why it has the value it has. It's one of those constants that sits at the foundation of physics, and just is. Like asking why the gravitational constant has the value it has, or why the fine structure constant is approximately 137. We can write it down, we can use it, we can't derive it from something more fundamental. If this kind of constant, or method, could be a sentence. This is actually deeply uncomfortable for physicists. A complete theory of everything, a theory that truly explains reality from the ground up, would ideally derive these constants from pure logic or from some deeper structure. We're not there yet. Maybe we never will be. But let's move on to something else that's strange about the speed of light, because there's a lot more strangeness to unpack here. Most people know that when you look at stars, you're looking into the past. The star you're seeing isn't where it appears to be, it's where it was when the light that's hitting your eye right now left it. For nearby stars, that's a few years. For distant ones, thousands or millions of years. For galaxies at the edge of the visible universe, billions of years. This is usually presented as a kind of cool fact. Stargazing is time travel, and it is. But the deeper implication is usually glossed over, because the speed of light isn't just limiting how fast we can travel, it's limiting how fast we can know. It's limiting how fast cause can become effect. The universe, at its most fundamental level, is finite in how quickly it can communicate with itself. Think about that. The universe is a thing that exists in space and time, and it cannot know its own state instantaneously. The right side of the universe doesn't know what the left side of the universe is doing right now. There is no right now that spans the entire universe, because by the time any signal could travel from one region to another, time has passed. This isn't just a limitation of our technology, it's a feature of the universe itself, a structural property. The universe is in some sense fundamentally local. What happens here can only affect things over there after a minimum delay, and that delay is set by the speed of light. Now here's where it connects to something most people haven't heard of, and which I find one of the most haunting ideas in all of physics. The observable universe, the part of the universe we can see, has a boundary. We call it the cosmological horizon, or sometimes the Hubble sphere, or the particle horizon. It's the region from which light has had time to reach us in the approximately 13.8 billion years since the Big Bang. The current radius of the observable universe is about 46 billion light-years. Wait, 46 billion light-years? But the universe is only 13.8 billion years old. How can we see something 46 billion light-years away if light hasn't had time to travel that far? This is the expansion. The universe isn't static. It's been expanding the whole time. Space itself stretches. Light that left a region 13.8 billion years ago, from a point that was then relatively close to us, has been travelling ever since, but the space it was travelling through has been stretching the whole time. The source of that light is now much further away than it was when the light left. But here's the really haunting part. Beyond our cosmological horizon, beyond the roughly 46 billion light-year bubble we can see, the universe keeps going. Almost certainly, forever, or at least for distances so vast, they're functionally infinite. And it's out there right now. Stars are burning, galaxies are forming, things are happening. We will never see any of it. Not because our telescopes aren't powerful enough, not because we haven't waited long enough, but because the universe is expanding, and the expansion is accelerating. Space is growing faster and faster, and there's no reason to think it'll stop. There are galaxies out there right now whose light will never ever reach us, because the space between us and them is growing faster than light can cross it. This is one of the things I think about when I can't sleep. Not in a bad way, just in a how is this real way. Right now, in some galaxy 100 billion light years away, or 1 trillion, or 10 trillion, there are stars, there might be planets. There might be something looking up at its own night sky, just like we do, wondering if anyone else is out there. And they're out there, and we're out here, and neither of us will ever know about the other. Not because of any failing on our part, but because the speed of light, combined with the expansion of space, has made permanent strangers of us. That's the speed of light, as a barrier, not just of travel, but of knowledge, of contact, of shared existence. But let me shift gears, because there's another way the speed of light is strange that I haven't gotten to yet, and it's in some ways even more counterintuitive than everything I've described so far. It's about what happens as you approach it. Let's say you want to travel from Earth to some distant star. You build a rocket, an incredibly powerful rocket. You hit the throttle and you start accelerating. Faster and faster. You approach the speed of light. Here's what happens, according to special relativity. As you get faster and faster, as you approach the speed of light, it takes more and more energy to accelerate further. Not linearly more, exponentially more. The closer you get to the speed of light, the more energy you need to add, even a tiny bit more speed. At 99% the speed of light, you need enormous amounts of energy to get to 99.1%. At 99.9%, you need even more to get to 99.9%. The curve goes to infinity. To actually reach the speed of light, to hit 100%, you would need infinite energy. The universe doesn't have infinite energy available, so you can't get there. This is often described as you get heavier as you approach light speed, which is a somewhat outdated way of putting it. The more accurate thing to say is that your momentum, the quantity of motion you have, increases without bound. Not because your mass is literally growing, but because of relativistic effects on how velocity and momentum relate. But here's the interesting flip side. Massless particles, particles with no rest mass at all, move at exactly the speed of light, always. They can't go slower, they can't go faster. They exist in a completely different relationship with space and time. Photons, particles of light, have no rest mass. They move at sea, always, in a vacuum. And here's something genuinely strange about massless particles. From their own perspective, they don't experience time. Or more precisely, the math of special relativity, when applied to something moving at exactly the speed of light, gives a result where the photon's proper time, the time elapsed on its own internal clock, is 0 for any journey. A photon emitted by a star 10,000 light years away, which spends 10,000 years travelling through space before hitting your eye. From the photon's perspective, and I'm using that word very loosely, the journey took no time at all. It was emitted and absorbed instantaneously. There's something poetic about that. Light doesn't experience its own journey. It's just there and then somewhere else. Now let me tell you something about where the speed of light and gravity intersect, because this is a territory most people haven't fully explored, and it's where things get even stranger. We talked about special relativity, Einstein's 1905 theory, which deals with objects moving at constant speeds. But Einstein didn't stop there. In 1915, he published general relativity, which dealt with acceleration and gravity. And general relativity has a lot to say about light. The most famous thing general relativity predicts about light is gravitational lensing. Massive objects, stars, galaxies, clusters of galaxies, bend the fabric of space-time around them. And light, travelling through that curved space-time, follows curved paths. We can actually see this. When we look at distant galaxies, we sometimes see multiple images of the same galaxy, arced and distorted. Einstein rings, gravitational arcs, because the gravity of something in between is bending the light's path toward us. Galaxies acting as lenses for other galaxies. The universe bending its own light. This was first confirmed in 1919 during a total solar eclipse. Arthur Eddington led expeditions to measure the apparent positions of stars near the limb of the Sun. The Sun's gravity should, according to Einstein, bend starlight passing close to it, shifting the apparent positions of those stars slightly. It did. The measured shift matched Einstein's prediction, and not Newton's older, smaller estimate. Einstein became world famous overnight, not because he'd invented something, because starlight had bent the way he said it would. But here's the part about gravity and light that I find most viscerally strange. A black hole is a region of space-time where gravity is so extreme that the escape velocity, the speed you'd need to reach to get away, exceeds the speed of light. Nothing can travel faster than light. Therefore, nothing can escape. Not particles, not radiation, not information. The boundary of a black hole is called the event horizon. It's not a physical surface. There's no wall there, no material, just a threshold, a point of no return. Cross it, and the geometry of space-time curves so sharply inward that all possible paths lead only further in. You can't turn around, because turning around in that geometry means travelling faster than light, and that's not possible. Here's what I find profound about this. The black hole's trapping of light isn't about gripping light and holding it in. It's about warping the geometry of space and time so severely that the directions that lead outward simply cease to exist past the horizon. There's no outward anymore. Every direction leads deeper in. Light still moves at sea inside a black hole. It just can't go anywhere except toward the singularity, because in the warped geometry of the black hole's interior, that's the only direction time can go. Time, inside a black hole, points inward. You fall toward the singularity not because of a force pulling you, but because you're moving forward through time, and inside the event horizon, time itself points toward the center. Think about that slowly. The reason you fall into a black hole isn't primarily about force. It's about the direction of time. We talk about black holes as objects that travel past PMT, hollow. But maybe a better way to say it is, inside a black hole, the speed of light still governs everything, but the geometry of what that means has become so distorted that even moving at sea takes you nowhere useful. You're running at full speed inside a room whose walls are all made of the same floor. The speed of light isn't broken by black holes. The geometry in which the speed of light means anything is what's broken. And the boundary between those two geometries, the event horizon, is where the two regimes meet. It's where c goes from being sufficient to escape to being insufficient. A circle of just barely not enough. Now, I want to talk about one of the strangest things I know about the speed of light, and it involves asking what happens to the laws of physics if the speed of light had been different. Not slightly different, dramatically different. Because physicists have actually studied this. It's part of the field that tries to understand why our universe has the constants it has, and what they find is fascinating and unsettling in equal measure. The speed of light shows up in Einstein's most famous equation, E equals mc squared. That c, that's the speed of light. And that equation tells you how much energy is locked inside mass. The conversion factor between matter and energy is the speed of light squared. The speed of light is approximately 300 million meters per second. Squared, that's 90 quadrillion. That's 90 quadrillion joules of energy per kilogram of matter. That's why nuclear reactions, which convert tiny amounts of mass into energy using that formula, release such spectacular amounts of power. If the speed of light were 10 times smaller, the energy content of matter would be 10,000 times smaller. Nuclear reactions would be 10,000 times less energetic. The sun wouldn't shine. Not in the way it does, maybe not at all. If the speed of light were 10 times larger, a teaspoon of matter would contain, well, 10,000 times more energy than it does now. The sun would be unimaginably more violent. Stars would burn out in thousands of years instead of billions. The universe we know, and we in it, could not exist. The speed of light sits in a range of values that allows stars to shine at the right rate, for the right duration, for chemistry and biology to emerge. Whether that's meaningful, whether there's any reason the speed of light has the value it has, is a question that physics cannot currently answer. Some people find this deeply suggestive. Others find it deeply dangerous, the kind of thinking that leads toward anthropic reasoning and away from real science. I'll let you sit with it. What I'll say is, the speed of light isn't just a measurement we made. It's a structural feature of reality, and its specific value shapes everything about the universe we live in. Now let me tell you about something called the cosmic speed limit from a completely different angle. Because I've been talking about the speed of light as a limit, but there's something more subtle going on that I want to try to explain. The speed of light isn't just the fastest anything can move. It's the speed at which anything with no mass must move. It's the speed of causality, the speed at which the universe communicates with itself. Here's an analogy I like. Imagine a very large pond. You drop a stone in the middle. The ripples spread out at a particular speed, the speed of waves in that pond, set by the water's depth and tension and density. Everything about how information spreads in that pond is governed by that wave speed. Now, someone at the far end of the pond wants to know what you did. They can't know until the ripples reach them. The pond communicates with itself at wave speed. The universe is the pond, the speed of light is the wave speed, and the universe communicates with itself. Causes produce effects, fields change, particles interact at that speed and no faster. But here's the thing. The wave speed in a pond isn't a law that was imposed on the pond from outside. It emerges from the properties of the pond itself, the water, the depth, the physical constants of the material. The pond is its own speed limit. The speed of light is like that. It's not imposed on the universe from outside. It emerges from what the universe is made of, from the properties of space and time themselves. It's written into the structure. Maxwell's equations, those equations describing electromagnetism, naturally produce a speed. That speed is the speed of light. In those equations, the speed comes from the relationship between two constants, the electric permittivity of free space and the magnetic permeability of free space. These constants describe how strongly space responds to electric and magnetic fields. The speed of light is mathematically derived from them. So, in a sense, the speed of light is as fast as electricity can push and magnetism can pull. In the medium of space itself, it's a property of the vacuum. And again, why does the vacuum have those properties? That's where we hit a wall. We know that it does, we can measure the constants, we can derive the speed from them, but we can't yet explain why those constants have the values they do. This is actually what makes physics so philosophically alive right now. We're in a period where we can describe reality with extraordinary precision. We have the Standard Model and general relativity, two theories that together explain almost everything we observe, and they're spectacularly accurate. But there are things sitting underneath both theories. Things like, why does the speed of light have this value that neither theory can touch? Something's missing, something deeper, and nobody knows what it is yet. Now, I want to shift into some territory that might feel more familiar, but which I think is worth exploring because of how it reframes the speed of light. Most people know that the speed of light is slow on cosmic scales, that it would take 4 years to reach the nearest star, 100,000 years to cross the Milky Way, 2.5 million years to reach Andromeda. But let me give you a few numbers that might land differently depending on how I present them. Light travels about 300,000 kilometers in 1 second. That means, in 1 second, a photon of light could circle the Earth about 7.5 times. 7.5 laps around the entire planet in 1 second. That's fast. That's really, really fast by any human standard. But the Sun is 150 million kilometers away. Light takes about 8 minutes and 20 seconds to cover that distance. Not 8 seconds, 8 minutes. If the Sun suddenly turned off, just stopped, we wouldn't know for 8.5 minutes. We'd still see it shining, we'd still be receiving its warmth, and then, 8 minutes and 20 seconds after it went dark, we'd see it disappear. And the Sun is our nearest star, our near neighbour. The next nearest star system, Alpha Centauri, is about 4.2 light years away. Light years, that's the distance light covers in an entire year, at 300,000 kilometers per second from entire year. 4.2 of those, that's about 40 trillion kilometers. Haughty, followed by 12 zeros. If you were to drive there in a car, going 100 kilometers per hour, the journey would take roughly 45 million years. That's about as long as it's been since the dinosaurs went extinct. You'd leave Earth while the Tyrannosaurus Rex was still alive, and you'd arrive while it was already a 45 million year old fossil. That's how far away our nearest neighbour is, and light covers it in 4 years. Our galaxy, the Milky Way, is about 100,000 light years across. Even at the speed of light, crossing it takes 100,000 years. That's longer than modern humans have existed. We've had civilization for maybe 10,000 years. Written language for maybe 5,000. The speed of light, fast as it is, would need 20 civilizations worth of time just to cross our galaxy. And we're an average galaxy. There are galaxies out there, the IC 1101 for instance, that are over 5 million light years across. To cross that galaxy at light speed would take 5 million years. The entire evolutionary history of the human genus, from early Homo to us, is about 2.5 million years. You'd need 2 of those just to cross one galaxy. The observable universe, as I mentioned, is about 93 billion light years in diameter. 93 billion years at light speed. The universe is only 13.8 billion years old. The observable universe is so large that even at the speed of light, you couldn't cross it in the entire age of the universe. And beyond the observable universe? Who knows? Current cosmological models suggest the full universe might be at least 250 times the size of what we can see. Maybe many, many more times than that. Maybe infinite. Speed of light, fastest possible. And the universe is so vast that it barely makes a dent. Here's something that I think about sometimes, and that I think is worth sitting with for a moment. We talk about how vast space is, about how long these journeys would take, but we almost never ask the more personal version of this question. What does this mean for the possibility of connection between different civilizations? Let's assume for a moment, and this is speculative, I'll say that once. Let's assume there are other intelligent civilizations in our galaxy. Not a crazy assumption. The Milky Way has hundreds of billions of stars. Many have planets. The chemistry of life uses atoms and molecules that are everywhere. It would be statistically strange if we were alone. But even if there's a civilization 1,000 light years away, not that far, on galactic scales, the nearest they could ever communicate with us is 1,000 years from now, assuming they sent a message today. And then our reply wouldn't arrive for another 1,000 years. A back and forth conversation would take 2,000 years per exchange. Humans have had complete civilizations rise and fall in 2,000 years. Rome, from republic to empire to fall, is roughly 1,000 years. The entirety of medieval Europe is roughly 1,000 years. One exchange, one question and answer at the speed of light with our nearest hypothetical neighbour, we would not be having a conversation. We would be sending letters that our descendants would receive and reply to, and their descendants would reply to, and maybe 5,000 years later, something like a dialogue might exist. But the civilization that sent the first message would be unrecognizable by the time the second reply came back. The speed of light doesn't just make space travel hard. It makes civilization-scale communication effectively impossible across interstellar distances. Not just slow, functionally impossible in any meaningful human time sense. And this, combined with the sheer scale of space, is one of the reasons many scientists find the silence of the cosmos so unsurprising. Not because life is probably rare, but because even if it's common, The speed of light ensures that civilizations are essentially isolated from each other. Every civilization is an island, separated by light-year-wide oceans, able to see the distant lights of other islands, but unable to reach them or speak to them in anything resembling real time. This is profound, and I think it's under-discussed. Now let's go back inside the physics for a bit, because I've been circling around something, and I want to get right into the center of it. Einstein's special relativity tells us that the speed of light is constant for all observers. That leads to time dilation and length contraction. That's weird. Very weird. But there's something even more unsettling buried inside the math. It's called the relativity of simultaneity. And this one, I think, is the strangest implication of the constant speed of light. Stranger than time dilation, stranger than length contraction. Here's the setup. Imagine a long train car moving along a track. There's a person standing exactly in the middle of the car. At exactly the moment they pass a person standing on the platform outside, two lightning bolts strike, one hitting the front of the train and one hitting the back, simultaneously. Now, the person on the platform sees the lightning bolts hit at the same time. They're equidistant from both points. The light from both bolts arrives simultaneously. They conclude, the lightning bolts hit simultaneously. Straightforward. The person in the middle of the moving train know they're also equidistant from the front and back of the train car, but they're moving toward the front, so the light from the front bolt reaches them first. The light from the back bolt reaches them after, and since the speed of light is constant, the same for them as for the platform observer, they conclude from those arrival times that the front bolt hit first. Same two events. One observer says they happen simultaneously. One says the front one happened first. Both observers are correct. Both are making valid measurements. There is no fact of the matter about which one is right. The events are simultaneous in one reference frame and non-simultaneous in another. There is no absolute now. There is no universal present moment. Think about what that means. Right now, somewhere across the universe, something is happening. That statement is undefined, meaningless. There's no universal right now. Different observers, moving at different speeds, will have different answers to what's happening. Right now, in some distant galaxy, this isn't a philosophical position. It's a mathematical consequence of the speed of light being constant. The constancy of c directly implies the relativity of simultaneity. You can't have one without the other. And once you accept this, once you really absorb it, the universe starts to look very different. Not as a thing that exists in a single share present moment, with a universal now ticking forward for everyone, but as a four-dimensional structure, a block of space-time, in which events are located at specific space-time coordinates, and different observers slice through that block at different angles, each creating their own experience of time passing, and now. This is called the block universe, or eternalism. The idea that the past, present and future all equally exist, that now is just the moment your particular slice of space-time intersects with any given event. That the future is as real and fixed as the past. That time doesn't flow in any fundamental sense, but rather that we move through it. Is this true? I don't know. Neither does anyone else, definitively. It's a deeply contested question in the philosophy of physics, but it follows more or less naturally from taking the relativity of simultaneity seriously. And the relativity of simultaneity follows from the constant speed of light. One constant, one fact about the universe, and it unravels our entire notion of time. And I want to stay with the block universe for a moment. because I don't think we give it enough credit as a genuinely strange idea. Most of us walk through our days with a feeling, a deeply intuitive feeling, that the present moment is special, that now is real in a way that the past is not, and the future is not. The past is gone, the future hasn't happened. But now, this moment, this instant, is real, is happening, is where we live. The relativity of simultaneity says that feeling is correct for you, locally, but it doesn't generalize. It doesn't extend to the universe. The person a billion light years away, moving at a different velocity than you, has a different now. Their present moment slices through space-time at a different angle. What is the future for you might be the past for them, for distant events. There's a thought experiment sometimes called Andromeda, and it makes this disturbingly concrete. The Andromeda galaxy is about 2.5 million light years away. Two people standing side by side on Earth, one walking toward Andromeda, one walking away from it, disagree about what is happening right now in Andromeda by thousands of years, walking, not flying, not moving at significant fractions of light speed, just walking. The two people are essentially at the same point in space. They disagree about events in Andromeda by thousands of years. Both are right. There's no fact of the matter. This isn't a paradox. It's not a contradiction. It's just what the constant speed of light implies about the structure of time. It's not that time is an illusion. It's that time, as a universal thing, is the illusion. What's real is space-time. Relationships between events, causality, the interval, and the speed of light is at the center of all of it. Okay, I want to talk about something completely different now. Because all of this has been about why the speed of light creates limits and weirdness. But there's a question I haven't addressed yet, and it's maybe the most natural question. What if the speed of light could be different? What if, in some sense, it can be different? Here's a thing that sounds impossible but is real. Light doesn't always travel at sea. In a vacuum, yes, always. But in a medium, glass, water, air, diamonds, light slows down. In water, light travels at about 75% of its vacuum speed. In glass, about 60 to 70%, depending on the type of glass. In diamond, one of the densest refractive materials, light slows to about 41% of its vacuum speed. Slower than sound is to air, proportionally speaking. This slowing is why lenses work. It's why prisms work. It's why a straw looks bent in a glass of water. The light bends when it enters a slower medium, because different parts of the wavefront enter the medium at different times and slow down at different rates. Now, the thing is, in a medium, light isn't actually slowing down in the deepest sense. Photons are still moving at sea between interactions, but they're constantly being absorbed and re-emitted by atoms in the material. That absorption and re-emission takes a tiny bit of time, and that accumulated delay gives you an effective speed that's slower than c. But here's something genuinely astonishing. In 1999, a physicist named Lean Hell slowed light down to 17 meters per second, walking pace. You could literally outrun it. She did this using a Bose-Einstein condensate, a state of matter that exists only near absolute zero, where atoms collectively enter the same quantum state and behave as one. In this exotic medium, The interaction time between photons and atoms was so extended that the effective speed of light dropped to 17 meters per second. I think about this sometimes, and I genuinely can't figure out how to feel about it. The thing that's supposed to be the fastest anything can move, a cosmic speed limit, being walked past by a jogger in a specific medium under extreme conditions. But still. Later, Howe's team slowed light to complete stop. They encoded information into light, brought the light pulse to zero velocity inside the condensate, held it there, and then re-released it. They stopped light. Now, and this is important, this doesn't violate any of what we've been talking about. The information can't travel faster than c. The slowing happens because of the medium, not because light itself has changed. The speed of light in a vacuum, the fundamental constant, is still 299,792,458 meters per second. Nothing has changed about that. But the demonstration is viscerally strange. Something we treat as almost synonymous with speed, light, being frozen in place in a laboratory in Cambridge, Massachusetts. There's a flip side to this, by the way. If you can slow light below the speed at which particles travel through that same medium, something remarkable happens: Cherenkov radiation. When a charged particle moves through a material faster than light moves through that same material, not faster than c, the vacuum speed, but faster than the local effective speed in that medium, it creates a kind of electromagnetic shock wave, the optical equivalent of a sonic boom, a cone of blue-white light radiating outward. This is what gives nuclear reactors their characteristic ghostly blue glow when viewed through the water that surrounds them. The radioactive particles being produced are moving faster than light moves through water, so they're producing Cherenkov radiation constantly. That ethereal science fiction blue is the light equivalent of a sonic boom, happening over and over and over inside the reactor core, something moving faster than light, in water, right now, in reactors around the world. Again, this doesn't violate anything. The particles are still moving slower than c, they're just faster than the local effective speed of light in that medium. The fundamental limit is untouched, but the visual is deeply strange. A particle punching through water faster than light can follow, and in that gap, that impossible seeming gap, blue light, like a ghost, marking the path where it's been. Let me tell you about one more strange thing about the speed of light, and then we're going to start coming back down. Quantum mechanics. Because all of this so far has been about special relativity, Einstein's 1905 theory. But there's another pillar of modern physics, quantum mechanics. And quantum mechanics has something strange to say about the speed of light, too. One of the most famous results in quantum mechanics is entanglement. Two particles can be prepared in a shared quantum state, such that measuring one immediately affects the measurement outcome of the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he hated it. He spent years trying to show that it couldn't be real, that there had to be some hidden variables, some information stored locally in each particle that explained correlations without any faster-than-light influence. He was wrong. We know that now. John Bell's theorem, published in 1964, gave a way to test whether hidden variables could explain entanglement correlations. And experiments, especially Alana Spexer's experiments in the 1980s, and more definitive versions since, have conclusively shown that no local hidden variable theory works. The correlations are real, they're not explained by local information. When you measure an entangled particle, something happens, something is resolved. That is instantaneously correlated with what would happen if you measured its partner, regardless of distance. What we can do is to think about or, but here it is, you cannot use entanglement to send information. What we can do is retangle them within the combination of things like, the correlations are real. When you measure your particle, you get a random result. Your partner gets a correlated result, but neither of you can choose what result you get. There's no way to encode a message in the random outcomes. There's no way to signal. The universe seems to have set things up so that entanglement is real and instantaneous, but also perfectly arranged so that it can't be used to send faster than light information. It's like there's a correlation at spooky non-local distances, but reality is carefully set up so that you can only discover the correlation after the fact, when you compare notes through a normal light speed limited channel. Whether this is a coincidence or a deep principle is again one of those questions sitting at the frontier where physics and philosophy blow together. Some physicists think entanglement is revealing something about the structure of space and time that we haven't fully grasped yet. That the non-local correlations are pointing toward a deeper theory where space and locality are emergent properties, not fundamental ones. Where the speed of light as a limit on information transfer follows from something deeper that we haven't found yet. Others think it's just what it is. Quantum mechanics is non-local in a technical sense but causal in the operational sense, and that's fine, and we don't need to read more into it. I find myself fascinated by the former possibility without being able to commit to it. The honest answer is, we don't know. And in this context, we don't know is one of the most interesting sentences in science. There's one more frontier I want to touch on here, and it's speculative. Let me be clear about that up front. But I think it's worth naming because it lives right at the edge of what we know, and because it connects back to the question of whether C is truly fixed. Some physicists have asked, is the speed of light actually constant? Not just across space, but across time, across the history of the universe. It's a serious question. There are cosmological puzzles, most famously, the horizon problem, that inflation theory was designed to solve, but that some researchers have proposed could instead be solved if the speed of light was much higher in the very early universe and has since settled to its current value. This is called varying speed of light theory, and it's controversial. Genuinely controversial. Most physicists are skeptical, but it hasn't been definitively ruled out, and several researchers have proposed ways to test for it. The deeper question underneath that one is, if C can vary, what does that mean? What is C, actually, in terms of the fabric of space-time? If it's truly fundamental, baked in, it can't vary. If it's emergent from something deeper, maybe it could. We don't know. What we do know is that C has measured everywhere we can reach, has tested to extraordinary precision in experiments on Earth, and in observational data from distant quasars, appears to be constant, stable, the same. For now, at least, the universe holds its signature steady. Let me talk about the light cone. because I've mentioned it in passing, but it deserves more than a mention. It deserves its own moment, because it might be the most important geometric idea in all of physics. Draw a dot on a piece of paper. That dot is you, right now, at this moment in time, this particular location in space, this particular instant. Now draw lines extending from that dot, lines going outward in all directions, but also upward, representing the passage of time. At the speed of light, spreading through space as time passes. The result in 3 dimensions would look like an hourglass, a cone opening upward into the future and a cone opening downward into the past. This is your light cone. Everything inside the future cone, every event that you could possibly reach, every region of space you could affect by sending a signal or travelling there, is your causal future. Anything you do right now can, in principle, influence events inside that cone. What you do in the next hour can affect your neighbourhood. What you do over a lifetime can affect a slightly larger region. What humanity does over centuries can, by sending signals, affect stars tens of light years away. The cone expands as time increases, but it's always bounded. It always has walls. Those walls are made of light. Everything inside the past cone, every event that could possibly have caused what's happening to you right now, every signal that could have reached you, is your causal past. The whole history of the Earth, the history of the sun's light on your planet, signals from stars that left thousands of years ago and finally arrived at your eye last night, all of that is inside your past light cone. And everything outside both cones, everything to the side, so to speak, in space-time, is causally disconnected from you at this moment. Events happening right now, but far enough away that even light couldn't have connected you. They can't affect you, you can't affect them. They are, at this moment, in no meaningful causal relationship with you whatsoever. This structure, the light cone, is the scaffolding of causality. It's the shape of what can matter to what. Every particle, every atom, every human being, every star has one, and the walls are always made of light, always moving outward at exactly C. Here's what's beautiful about this. The light cone isn't just a physicist's tool, it's a physical reality. When we say that no signal can travel faster than light, what we're really saying is that causal influence can't escape the light cone. The cone is the boundary of influence, the shape of possible futures, the geometry of commercial action. Because, and when you stack all these light cones together, every event in the history of the universe, with its own cone of causal influence spreading forward and backward in time, you get something that looks almost like a web. A vast overlapping network of causality. Some events are connected, some are forever apart, and the threads between them are all made of light. I find this almost unbearably beautiful. The universe isn't just a collection of things. It's a collection of events, connected by light, structured by causality, woven into a four-dimensional tapestry where every thread travels at exactly C. That's not metaphor, that's geometry. There's a version of this that matters enormously for the very large scale. As the universe expands, as space between galaxies grows, objects that were once inside each other's light cones can drift out of them. Galaxies that once could have traded signals, that once could have influenced each other, find that the expanding space between them means new signals will never arrive. They are, gradually, falling out of causal contact. The future light cone of any given galaxy reaches less and less of the universe as time goes on. In the very far future, we're talking trillions of years from now, the night sky will be empty. Not because stars have burned out, though many will have. But because the galaxies beyond our local group will have receded so far that their light will never reach us, they'll vanish beyond the cosmological horizon, one by one. The observable universe, which today contains hundreds of billions of galaxies, will eventually contain only the few dozen galaxies gravitationally bound to us in our local group. The rest will be gone, not destroyed, but beyond reach, cut off, causally disconnected. Future astronomers, if there are any, will look up at a much darker sky and have no way of knowing that the universe was once full of galaxies. The evidence will be gone. The light that carried that evidence will have been stretched by expansion until its wavelength becomes infinite, until its energy becomes zero, until it simply ceases to exist as a detectable signal. The history of the cosmos will be literally unreadable. We live in a privileged moment, not just in the sense that the Earth is comfortable for life, but in the sense that we can still see the full story. We can still read the light from the early universe. The cosmic microwave background, the afterglow of the Big Bang, is still detectable. The distant galaxies are still visible. The story is still there to read. The speed of light set a timer on how long that window stays open. And the timer is running. Let me tell you about the Doppler effect and what it tells us about the universe, because it connects directly to what we've been discussing and leads somewhere genuinely surprising. You've heard the Doppler effect with sound. An ambulance siren sounds higher pitched as it approaches you and lower pitched as it drives away. The sound waves compress as the source approaches, higher frequency, higher pitch, and stretch as it recedes, lower frequency, lower pitch. Light does the same thing. If a light source is moving toward you, its light shifts toward the blue end of the spectrum, shorter wavelength, higher frequency. If it's moving away, it shifts toward the red end, longer wavelength, lower wavelength. This is called blue shift and red shift. In 1929, Edwin Hubble published observations showing that almost every distant galaxy in the sky was red-shifted. And not just slightly, the further away a galaxy was, the more red-shifted its light was. The further away, the faster it seemed to be receding from us. This was the discovery that the universe is expanding. Not that galaxies are moving through space away from us, but that space itself is expanding, carrying the galaxies with it. Like raisins in a rising loaf of bread, the raisins aren't moving through the dough is growing, and every raisin sees every other raisin moving away from it. Now, the redshift of distant galaxies isn't just a curiosity, it's a tool. Because light carries information, and the stretching of that light tells us exactly how much the universe has expanded since the light was emitted. The light from a galaxy with a redshift of 1 has had its wavelength doubled during its journey, meaning the universe has doubled in size since that light set off. The furthest objects we can see, the earliest galaxies, the quasars at the edge of the observable universe, have redshifts so large that the light we're seeing was emitted when the universe was only a fraction of its current size. We are, in a real sense, looking at the universe in its infancy. The speed of light is a time machine, and the machine works backward. The further you look, the older the picture. But here's the thing that makes this cosmically strange. The most distant light we can see, the cosmic microwave background, the afterglow of the Big Bang itself, left its source when the universe was about 380,000 years old. That's early. The universe is 13.8 billion years old now. We're seeing it as an infant, and that infant universe looks, in every direction, almost perfectly uniform. The same temperature, the same density, nearly identical in all directions, to 1 part in 100,000. Why? How did regions of the universe that were never in causal contact that were, at the time the CMB was released, so far apart that light from one could never have reached the other, somehow end up at the same temperature. If two things reach the same temperature, it's usually because they were in thermal contact. They exchanged energy. But the early universe's horizon was smaller than the universe itself. There were regions that had never exchanged a photon, never been in causal contact, never been connected by any signal. And yet, they had the same temperature. This is called the horizon problem, and it's one of the deepest puzzles the speed of light creates for cosmology. Because c limits how far information could have travelled, and the universe seems too uniform for a universe in which information travels at c. The leading solution is cosmic inflation, the idea that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, so rapid that regions which had been in causal contact were suddenly hurled far apart. They reached thermal equilibrium first, then expansion separated them. The uniformity is a fossil from before inflation, preserved despite the expansion. If inflation happened, and the evidence for it, while indirect, is substantial, then the speed of light also defines the scale of the problem inflation was invoked to solve. The horizon problem is a problem because of c. The solution is a moment when the universe briefly acted as if c didn't constrain expansion, because it's space itself that expanded, not anything moving through space. The speed of light limits how fast things can move through space. It doesn't limit how fast space itself can expand. That distinction matters more than almost anything else in cosmology. Space can expand faster than light. It does, in fact. The most distant galaxies are receding from us faster than light right now. Not because they're moving faster than light, but because the space between us is growing faster than light can cross it. They're not breaking any rules, they're just being carried by the expansion of the medium itself. An inflation may have been an extreme version of this, a brief, violent expansion of space that dwarfed anything happening today. A moment when the universe grew from something smaller than an atom to something larger than a galaxy in a fraction of a second. The speed of light was never violated. Space just grew. I find this distinction endlessly fascinating. C is not a limit on space. It's a limit on causal influence within space. Space can do whatever it wants. It's the signals, the particles, the fields, the information. Those are the things that can't beat c. Space itself is under no such constraint. The universe is stranger, as a result, than the naive version of nothing goes faster than light suggests. Space goes faster than light, quite routinely, in the expanding cosmos. We just can't use it to send a message. Here's something about the nature of light itself that I haven't addressed yet, and which I think is essential to really understanding why the speed of light is what it is. What is a photon? I've been saying light and photons somewhat interchangeably, but there's a real question buried here. Light is both a wave and a particle. You've heard this probably. But let's spend a minute on what that actually means, because it's not just a curiosity, it's directly tied to why light travels at sea. In the early 20th century, physics discovered that light, when it interacts with matter, when it's emitted or absorbed, does so in discrete chunks. Quanta, packets of energy. These packets are photons. The energy of each packet depends on the frequency of the light. Blue light carries more energy per photon than red light. X-rays carry more than visible light. Radio waves carry less. that between interactions, when it's just travelling, light behaves like a wave, a spreading, oscillating disturbance in the electromagnetic field. Not a discrete particle tracing a single path, but a wave spreading in all directions, interfering with itself, producing the patterns of diffraction and interference that prove its wave nature. This dual nature, particle when it interacts, wave when it travels, is genuinely strange. It's not that light is sort of a wave and sort of a particle. It's that it's fully both, depending on what you're asking. The question, which is it really, doesn't have an answer, because the answer depends on the type of observation. Now, why does this matter for the speed of light? Photons are massless. We established that. They have to travel at c. But why do they have to travel at all? Why can't a photon just sit still? This is where quantum field theory, the deepest framework we have for understanding particles, has something to say. In quantum field theory, a photon is an excitation of the electromagnetic field, not an object moving through a background. An oscillation in the field itself, and that oscillation propagates at the speed determined by the field's properties. The electromagnetic field permeates all of space. It has a certain tension and a certain inertia, described by those permittivity and permeability constants I mentioned earlier. These properties determine how fast oscillations in the field propagate. They set c. A photon cannot sit still, because a photon is a propagating wave in a field, and fields propagate at the speed their properties dictate. It's a bit like asking why a ripple on a pond can't stay in one place. It can't, because a ripple is by definition a propagating disturbance. The moment it stops propagating, it ceases to be a ripple. A photon is like that. It ceases to be a photon if it stops moving. Its very existence is motion. Its very identity is travel at c. This is a strange and deep fact. The particles of light are not things that happen to move fast. They are things whose existence is speed. Remove the motion, and the photon is gone. And that, I think, is the most fundamental answer to why does light travel at the speed of light? Because light is the electromagnetic field propagating, and the electromagnetic field propagates at c, and that propagation is not something the field does, it's something the field is. Let me talk about time travel, because by this point in the video, you might be wondering about it, and I don't want to leave it unaddressed. Here's the thing about traveling through time, specifically about traveling forward in time faster than normal. It's not science fiction, it's physics, and the speed of light is how you get there. Time dilation means that a clock moving at high speed runs slow relative to a stationary clock. Not metaphorically slow, literally, physically, measurably slow. A clock that spends time moving at 99.9% the speed of light will accumulate less time than a clock that stays still. This means that if you were to travel at close to the speed of light for what felt to you like a year, you could return to Earth and find that many more years have passed there. Depending on how close to C you travelled, the discrepancy could be enormous. If you travelled at 99.9999% of the speed of light for say 10 years of your subjective time, you might return to find that thousands of years had passed on Earth. This is genuine forward time travel, not a paradox, not a philosophical loophole. Physics. You can't undo it. You can't go back. You'd arrive in your future, Earth's future, with no way to return to the present you left. But you'd be there. You'd have skipped over time that everyone else experienced, and the amount of time you skip is determined by how close to C you travelled. This is, in a strange way, one of the most hopeful things about the speed of light. We can't reach the stars in any reasonable time at human speeds. The distances are too vast. But if you could get close enough to C, the time dilation would compress the journey. From your perspective, it might not take as long as you'd think. You'd still be limited to light speed, you couldn't go faster. But the relativistic time compression means that a motivated traveller, in principle, could see a lot of the galaxy within a single human lifetime, as long as they were okay with leaving everyone they knew behind in the past. The catch, and it's a brutal catch, is the energy required. Getting to 99.9999% the speed of light requires energy so enormous that no rocket fuel we know of could provide it. The engineering is, with current technology, impossible by many orders of magnitude. Not just hard, impossible, in a we'd need to convert a significant fraction of the planet into fuel kind of way. But the physics works. The time dilation is real. We've measured it with atomic clocks on airplanes. We apply it in the design of particle accelerators, where particles are routinely boosted to 99.9999% the speed of light, and their lifetimes, as measured in the lab, are extended by factors of thousands compared to what they'd be at rest. So when people say time travel is impossible, they're usually thinking of travelling backward in time, which does seem to be prohibited by the laws of physics, though even this isn't fully settled. Travelling forward? That's just special relativity. That's just C. It works. It's real. It's happening in every particle accelerator on Earth. The universe allows you to skip forward in time. It charges you for it in energy, and it makes sure you can never come back. But the door is open. The speed of light is the key. And I think that's one of the strangest, most quietly profound things I know about physics. The law that prevents us from moving too fast through space is the same law that allows us to move faster through time. They're not separate. They're different faces of the same underlying structure, a trade-off built into the geometry of space-time. You can't have both. You can trade space for time, or time for space, but the exchange rate is fixed, and it's set by C. Before I bring this home, I want to acknowledge something. You may have noticed that this video keeps arriving at the same kind of destination, a question that physics can state precisely, but cannot yet answer. Why does C have this value? What determines the constants of nature? What is space-time underneath? Why does it have the structure that gives rise to the speed of light? This is not a failure of science. It's a description of where science currently lives. We are at the edge of something. There's a frontier in physics right now, maybe the most important frontier in the history of the subject, where the tools we have are exquisitely accurate, and the questions they leave unanswered are fundamental. Quantum mechanics describes the very small with staggering precision. General relativity describes gravity and the large-scale structure of space-time with equally staggering precision. Both theories are, in their domains, the most accurate scientific theories ever constructed. The predictions of quantum electrodynamics, the quantum theory of light and electrons, have been tested to 1 part in a trillion. 1 part in a trillion. That's like measuring the distance from New York to London to within a fraction of a millimetre. And yet, these two theories are incompatible. Their mathematical structures conflict. You can't simply combine them into a single theory of everything. At least, nobody has managed to, despite decades of effort. When you try to apply quantum mechanics to gravity, you get infinities, nonsensical results. The math breaks down. Something is wrong at the foundations, and we don't know what. The speed of light sits at the center of both theories. Special relativity, which gives us c, is baked into quantum field theory. General relativity is built on the same foundation. But the place where they fail to mesh is also the place where the deepest questions about c live. What is space-time? What gives it the property of propagating signals at this particular speed? Is c fundamental, or is it emergent from something deeper, something we haven't yet described? We don't know. And the "we don't know" here isn't polite academic hedging. It's a genuine statement about the frontier of human knowledge. The people who think about this for a living, some of the most brilliant people alive, don't know. String theory, loop quantum gravity, causal set theory, twistor theory, these are all attempts to find the deeper structure. None of them have been confirmed. None of them have made predictions we've been able to test in a way that decisively distinguishes them from alternatives. We are, right now, in a situation where we know the rules with extraordinary precision and don't understand why the rules are the rules. That's a strange place to be. It might be the most interesting place to be. Because the answer, when it comes, if it comes, is likely to reframe everything, including the speed of light, including what c actually is. Maybe c isn't a fundamental limit. Maybe it's an effective limit, an emergent property of a deeper structure, the same way temperature is an emergent property of molecular motion. Temperature feels fundamental until you understand that it's just average kinetic energy of particles. Maybe c will turn out to be like that, a macroscopic shadow of something microscopic, a sign pointing towards something deeper. Or maybe it is fundamental. Maybe when we finally find the theory underneath quantum mechanics and general relativity, c will still be there, irreducible, primary, unexplained, but exactly specified. The bedrock beneath the bedrock. I genuinely don't know which of those is true. I'm not sure anyone does. But sitting with the uncertainty, holding the question open without rushing to an answer, feels, to me, like one of the most honest things you can do with a question this deep. There's a quote attributed to Richard Feynman that I think about in this context. He said something to the effect that the first principle is that you must not fool yourself, and you are the easiest person to fool. In physics, that means being willing to hold the strange result and sit with it, rather than explaining it away with something comfortable and familiar. The speed of light is the same for everyone. Time dilates. Simultaneity is relative. The universe has a cosmological horizon we can never see past. These are strange. They feel wrong at first. The temptation is to reach for a story that makes them feel less strange, to domesticate them with analogy, to file them under interesting fact and move on. But the strangeness is the point. The strangeness is the signal. The universe is telling you something about its deep structure, and the thing it's telling you is, you didn't guess right the first time. That's okay. Neither did the smartest people in history. Aristotle was wrong. Newton was wrong, or rather, right in a limited domain and operating without the tools to see beyond it. Einstein was right enough to revolutionize physics twice and still couldn't fully accept what quantum mechanics was telling him. Being wrong at scale is the normal condition of human knowledge about deep things. What matters is being wrong in a way you can update from. The speed of light is one of the places where we updated, hard, completely, in a way that changed what we thought reality was, and we came out of it with something more true, more strange, more beautiful than what we had before. Here's the thing about the speed of light that I think is most important, and that tends to get lost in the wonder of the numbers and the experiments. The speed of light defines what is knowable for anyone, anywhere. Not just what's physically reachable, what's knowable. In the deepest sense, we can only ever know about regions of space from which light, or any signal, since they all travel at or below sea, has had time to reach us. We can only be affected by events that are within our light cone, the region of space-time that is causally connected to us. Everything outside our light cone, everything beyond the cosmic horizon, is unknowable in principle, not just in practice. There are parts of the universe that have been there the whole time, that are as real as anything here, but which have never, and will never, send us a single photon, never a graviton, never anything. Completely disconnected from us, forever. And we're completely disconnected from them. What happens there doesn't affect us. What happens here doesn't affect them. We're not neighbours, we're not even in the same universe, in any meaningful, operational sense. The speed of light writes the boundaries of what exists. For us, it defines our universe, not as the totality of everything that exists, but as the totality of everything that could ever matter to us. Everything within our forever expanding, but still bounded light cone. Everything else is a dark country we'll never visit and can't even see. There's something humbling about that. We live in the universe of incomprehensible scale. Hundreds of billions of galaxies in the observable part alone, and the observable part might be a tiny bubble in a vastly larger space. And even within our observable universe, almost all of it is permanently inaccessible, too far away to reach in any realistic sense, even at the speed of light. We're a species that, 100 years ago, discovered the universe was larger than our galaxy. 50 years ago, landed on the moon. 20 years ago, started detecting planets around other stars. And now we're just beginning to grasp what the speed of light really means for our place in all of this. The speed of light is not a minor inconvenience to be engineered around. It's not a temporary limitation that better rockets will overcome. It's written into the fabric of reality at the deepest level we can access. It's the rate at which the universe can know itself, the rate at which anything can matter to anything else. And yet, it's not zero. That's the other thing. If the speed of light was zero, if there were no causal propagation at all, there would be no universe. Nothing would influence anything else. No chemistry, no physics, no time, nothing. If the speed of light were infinite, if causality were instantaneous, the universe would be completely different. All events would instantly affect all other events. The universe would be, in some sense, a single undifferentiated thing with no local structure, no gradients, no complexity. It's the finite, non-zero, very large, but not infinite speed of light that makes the universe what it is. Complex, layered, structured, local. A place where things can happen in sequence, where cause can reliably produce effect, where patterns can form and persist long enough to build stars, planets, chemistry, life. The specific value of C is deeply enmeshed in what we are, in the fact that we exist, in the fact that we can ask questions, and that's either deeply significant or a complete coincidence, and I genuinely do not know which one it is. Most people miss this. They hear the speed of light, and they hear speed limit, and they think about how frustrating it would be to never reach the stars. And it is frustrating, in a certain light. But the same number that keeps us from the stars also makes the sun burn at the right rate to warm a planet for 4.5 billion years and let life evolve. E equals mc squared. That c, that constant, the energy of the sun is that constant squared times the mass the sun converts each second. Change the constant, change the sun. Change the sun, no us. You can't separate the frustration from the gift. They're the same thing. Let me dwell on E equals mc squared for a moment, because I think most people have heard this equation and not really absorbed what it's saying. Energy equals mass times the speed of light squared. That's the whole thing. 3 letters, 1 operation, one of the most consequential statements in the history of science. What it says is this: mass and energy are not different things. They're the same thing, expressed differently. Mass is frozen energy. Energy is liberated mass. They convert into each other at an exchange rate of c squared, which is, as we've established, approximately 90 quadrillion joules per kilogram. The implications of this are vast and strange. First, every object around you contains almost unimaginable amounts of energy. A litre of water, 1 kilogram, contains in principle enough energy to power a major city for years. The atoms in the water are not releasing that energy. The bonds holding them together are not being broken, but the energy is there, locked in the mass itself, accessible only if you could convert that mass entirely to energy, which we don't know how to do, but the energy is there. This is not a theoretical reserve, it's a physical reality. The energy is there in the same way that the height of a cliff represents potential energy. It's not doing anything right now, but the structure of physics says it's real. Second, E equals mc squared explains where the sun's energy comes from in the most precise possible terms. Every second, the sun converts about 4 million metric tons of mass directly into energy, not chemical combustion, which rearranges atoms, not fission, which splits them, but fusion, the merging of hydrogen nuclei into helium, in which the products are slightly less massive than the ingredients. That missing mass, 4 million tons of it every second, becomes energy, becomes light and heat and neutrinos, becomes the sunlight on your face. The sun is losing weight at 4 million metric tons per second. It has been doing this for 4.5 billion years. It has enough fuel to keep doing it for another 5 billion. That's the exchange rate c squared at work. The same constant that tells you nothing can reach c also tells you exactly how much energy is released when mass converts. It's the same constant, the same c, the same number. The speed of light is the conversion factor between mass and energy, and it is also the maximum speed of anything with mass, and it is also the thing that makes time relative, and it is also the boundary of the knowable universe. One number, one constant, woven into everything. I don't know what to do with that except sit with it. It's not useful in the direct sense. You can't leverage the beauty of the constant into anything practical. But I think there's something important about noticing it, about pausing to appreciate that the universe is at its foundations deeply integrated in a way that our ordinary experience doesn't prepare us for. That c isn't just a fast speed. It's a hub, a crossroads. Everything about energy and space and time and information runs through it. And we found it By accident, eventually on purpose, by looking at moons of Jupiter and tooth gears spinning in lamplight and clocks on airplanes and particles streaking through accelerators. We found the number at the center of everything. And we wrote it down. 299,792,458 meters per second. That's the speed of light. I want to sit with that a little longer, because I think there's more to say about what it means that the constant happens to be what it is. There's a philosophical framework called the anthropic principle, which comes in several flavors, from weak to strong. But the core idea is this: we can only observe a universe that is compatible with our existence. If the constants of nature were different, if C were wildly different, if gravity was stronger or weaker, if the fine structure constant shifted even a few %, then atoms wouldn't form, or stars wouldn't ignite, or nuclei would fly apart, and there would be no observers to do any observers. The universe we find ourselves in is by definition one that produced observers. So when we look at the constants and find them fine-tuned for complexity in life, we should not be surprised. We couldn't be here to notice if they were otherwise. Some people find the anthropic principle deeply satisfying, a clean resolution to the question of fine-tuning. Others find it philosophically hollow. It explains the observation without explaining the fact. Yes, we're here, so the constants allow us to be here. But why do they have those specific values? The anthropic principle doesn't answer that. It just points out that the question might be the wrong one to ask. There's a harder version, which involves the multiverse. If there are many universes, perhaps infinitely many, with different constants in each, then of course we'd find ourselves in one with constants that work. We'd have to. We couldn't exist in the others. This moves the mystery up a level. Instead of asking why C has this value, you ask why there are many universes with different values at all, and what determines the distribution. That's not an easier question. It might be harder, and it's currently by definition untestable. We can't access those other universes. I'm not trying to push you toward any particular view on this. What I want to convey is that the speed of light isn't just a curiosity. It's at the center of one of the deepest unsolved questions in all of science. Why is the universe the way it is, and not some other way? Why these constants? Why this C? We don't know. And the fact that we don't know is, I think, one of the most interesting things about being alive right now. We live in a moment where we have the tools to ask the question with real precision, and not yet the tools to answer it. That's a strange and exciting and humbling place to be. Let me leave you with something. You started this video knowing that light was fast. Maybe you knew the number. Maybe you knew something about relativity. But now, if this landed the way I hoped it would, you're sitting with something more uncomfortable. Not just light is fast, but light is what defines fast. Light is what defines now. Light is what defines knowable. Light is what defines us. We are made of matter, shaped by the laws that the speed of light helped create. We live on a planet warmed by a star whose energy comes from E equals mc squared. We navigate space using GPS satellites whose clocks must be corrected for relativistic effects. We look at the night sky and see the past. We live in a universe whose vast regions we will never see and can never reach. Not because of any failure of technology or imagination, but because the universe itself has a speed at which it can know itself. And that speed, that number, 299,792,458 meters per second, is simultaneously the most important constant in nature and one of the deepest mysteries in physics. We know what it is, we don't know why it is. We can use it, we can't transcend it. Somewhere out there, right now, in whatever sense right now can be said to mean anything across cosmic distances. Light is crossing space that has never been touched by any photon before. Stars are forming in regions we will never see. Civilizations, maybe, are waking up to a sky full of stars they'll never reach and sending signals that will never find us. And here we are, on a small planet, around an ordinary star, in one arm of one galaxy among hundreds of billions, with just enough curiosity to ask why the universe is the way it is, and just enough physics to barely start, to understand the answer. We are beings who evolved to navigate a world of walking speeds, throwing speeds, the speed of a spear and the speed of a river current. We are not built to feel the speed of light in our bones. We can't intuit it. We can't look at C and nod and say, yes, that feels right. We can only reach for it through mathematics and thought experiments and the slow, careful accumulation of evidence over centuries. And even then, we hold it at arm's length, half understanding. We're beings who evolved to navigate a world of walking speeds, throwing speeds, the speed of a spear, and the speed of a river current. We are not built to feel the speed of light in our bones. We can't intuit. We can't look at C and nod and say, yes, that feels right. We can only reach for it through mathematics and thought experiments and the slow, careful accumulation of evidence over centuries. And even then, we hold it at arm's length, half understanding. But here's what I find remarkable about that. We did it anyway. We are creatures made of atoms, assembled by evolution on one small planet, who decided to ask about the fabric of reality itself and got answers. Not complete answers. Not final answers, but real ones. Tested ones. Answers that work, that predict, that let us build GPS systems and nuclear reactors and gravitational wave detectors. We looked up from our little window of existence and mapped something true about the universe. Think about the arc of that story. For most of human history, we thought the Earth was the center of everything. Then we discovered it wasn't the center of the solar system. Then we discovered the solar system was one of billions in the galaxy. Then we discovered the galaxy was one of hundreds of billions. And that each step, the universe got bigger and we got smaller and more peripheral. And somehow, at each step, we kept asking questions anyway, kept building instruments, kept writing equations. And then we discovered that the speed of light is the same for everyone, and the universe broke open into something even stranger than the size alone suggested. Not just vast, not just old, but structured in a way that makes time itself relative, that makes simultaneity disappear, that places a fundamental limit on what any observer anywhere can ever know. And we figured that out from here, from this small planet, in this average solar system, in this unremarkable corner of one of billions of galaxies. Using brass gears and mirrors on hillsides outside Paris, and eclipses of Jupiter's moons, and atomic clocks on airplanes, and particle accelerators that fit inside university campuses. We figured out something true about the deep structure of reality. That's extraordinary. I don't want to let that become ordinary by saying it too quickly. It is extraordinary. The speed of light was hiding in plain sight for all of human history, in every candle flame, in every sunrise, in every beam through a dusty window, and we figured out what it was, what it meant, what it implied about the nature of time and space and the limits of knowledge. It took 300 years of increasingly precise measurement to nail down the number. It took 200 more years to understand what the number actually meant. It required a patent clerk in Switzerland to take two radical ideas seriously and follow them to their logical conclusion without flinching when the conclusion was that time itself is not universal. And the conclusion was true. It tested out. It worked. It described reality. That process, that long, stumbling, brilliant process, is one of the most important things our species has ever done. Not because it's useful, though it is. Not because it's beautiful, though it is. But because it represents something about what we are, at our best. Curious enough to ask, stubborn enough to keep measuring, brave enough to accept that the answer is strange. We are not the center of the universe. We are not exempt from its laws. We cannot transcend the speed of light or escape the light cone we were born into. We are, in the grand ledger of cosmic things, extremely small and extremely brief. But we looked at the light coming through the window, the same light that fell on every human who ever lived, and we asked, how fast is that? And we found out, and it changed everything. That is what the speed of light is. Not a speed limit, a signature. The universe's signature, written in the only ink it has, time, space, and the speed at which one becomes the other. And somehow, against all odds, we learn to read it.